Good morning, everyone, and welcome to our first ever Irrigation Innovation Consortium Headquarters Virtual Field Day. I hope you have your snacks and your pets all cuddled up, because today I get to take you on a lovely tour of our technology farm. Today we're going to be looking at a lot of research projects done by faculty and students from Colorado State University here at our facility. My name is AJ Brown, and I'm the Assistant Director of the Irrigation Innovation Consortium, and I also happen to be the Farm Manager and Station Director of this site. It is my pleasure today to welcome you to our farm. The irrigation sector is running into challenges that many other industries are facing with technologies, such as the scalability and cost effectiveness of implementing sensors in a way that becomes both usable and accurate for management decisions. Irrigation Innovation Consortium Headquarters was founded in 2018 as part of the initial foundation of the IIC as a whole. 2020 was our first research season where we were able to allow researchers to come on site and explore some of their research projects and their ideas and their innovations. Today I'm going to introduce you to some of the leading irrigation students and faculty from Colorado State University who are trying to meet some of those challenges by developing innovative, low-cost technological solutions in the irrigation space. And we can't develop new technologies without understanding the quality control needed to maintain accurate results for informed decisions. And so today we're also going to be hearing from one of our industry partners from the Irrigation Association, who's been working on quality controls for landscape controllers as well as flow sensors in the irrigation realm.
Hello, I'm Brent Meekum, recently retired from the Irrigation Association as the Industry Development Director. And I'm here today at the Irrigation Innovation Consortium to talk about some of the new technology that's been in the marketplace for controlling landscape irrigation. The testing of what are called smart controllers, or weather-based irrigation controllers that automatically change the irrigation schedule based upon the weather. They're all unique, and this is probably one of the challenges for the landscaper in the marketplace, is being able to be familiar and technical enough with every kind of technology that's here. Some of them are very low end. This controller has been in the marketplace for a really long time, but it has an add-on device, so it's measuring the conditions on site. And then you have some that are very sophisticated and what we would consider a high-end type of controller, where it's relying on information from either a satellite, cellular, Wi-Fi connection of some kind. The purpose of this study, it really is to validate how well did the controllers perform in a very difficult testing condition, managing 6 different landscapes simultaneously, and then to say which are the best performing controllers. So one of the challenges has been is that while all of these controllers have been WaterSense labeled and certified through the EPA program, it's only a 30-day test, and we want to know, well, how well did they perform over a longer period of time throughout the growing season. There are many municipalities that probably are looking at the idea that it's not just good enough to put on the right amount of water, but also to put the water on when it's actually needed. And that's currently what we're really striving to test. So it's been a very challenging. We have found some great results. I think sharing this with the manufacturers, they can look at their own protocols and algorithms of how their product performs. And the intent is hopefully to see improved performance over time, and also to give confidence to the industry that these products really do work in saving water in the urban landscape. So one of the other studies that I'm going to talk about today is flow measurement and flow management, and how is that incorporated into landscape irrigation. And we created a testing protocol through the Smart Water Application Technologies Initiative of the Irrigation Association. And so I had the opportunity to try and test the testing protocol to find out what things worked well and what things might be improved as it goes forward to maybe become a standard for landscape irrigation products. The testing protocol that we created was agnostic towards the type of technology. What we really wanted to validate was whatever the manufacturers claim the capability of their flow sensor would be. And this has been actually very useful because currently there are no testing standards for flow sensors in the irrigation industry. Well, thank you for allowing me to take a few minutes of your time today to talk a little bit about the flow sensing technology study that we've been doing. And it's an opportunity now for me to introduce Jose Chavez, professor at Colorado State University. Take it away, Jose.
My name is Jose Chavez, and I'm an associate professor at the Civil and Environmental Engineering Department at Colorado State University. I'm here at the IIC as part of a very interesting project. We are involved in evaluating different algorithms for crop evapotranspiration estimation using remote sensing. The overall idea is to update irrigation scheduling algorithms for deciding when to irrigate, like the well-known WISE irrigation schedule tool. We have net radiometers as well, and an array of other sensors that will be explained fully by Edson.
Hello, my name is Edson Costa Filho. I've been working in this project on updating WISE using remote sensing techniques. And the data collection that we have for this project basically relies on three components: the remote sensing, the weather data, and the heat fluxes. So for latent and sensible heat fluxes, we have a very cool system installed in this site. That's the eddy covariance tool. And it's just a network of sensors that can provide with especially average sensible heat and latent heat fluxes. The eddy covariance is a system that's been collecting data every 15 minutes as an average. And all the other sensors also are collecting data every 15 minutes on average. And the idea is to use all those heat fluxes measurements to compare to our surface energy balance approach. And for future implications, the idea for this project is not to just be done in this exact time frame, but to be expanded in the sense that we can engage with local farmers and bigger fields to apply the methodology and to show people that WISE combined with remote sensing will provide us with a better tool for irrigation scheduling. Up next, we're going to hear from Matt Lurtz. He's also a PhD student in the Civil Engineering Department at CSU, and he'll be talking about stochastic modeling of ET.
Hello everyone, my name is Matt Lurtz. I'm a fourth-year PhD candidate at Colorado State University in Civil and Environmental Engineering. Dr. Tim Gates and Dr. Ryan Morrison are my advisors, and today I'm going to be talking about a low-cost DIY ecosystem monitoring station. The main objective of my research is to essentially test the durability and longevity of the low-cost DIY sensors that have been applied in this agricultural ecosystem. We want to test the durability and longevity of these sensors to see how autonomous they can be in order to determine if they're going to be applicable in more remote areas where cell communication is lower and battery power is a concern. The future directions of this research are to deploy these sensors and to test these sensors again in a natural ecosystem in southeastern Colorado, essentially in a more remote location. Another direction will be to take the data collected here and analyze it within a stochastic framework. Up next, we have PhD student Maria Capurro, who works for Dr. Alan Andalas.
Hello everyone, my name is Maria Cristina Capurro. I'm a PhD student from Colorado State University, working at the Soil and Crop Department with Dr. Andales and Dr. Ham, and in particular in this project also with Dr. Kuhnberg. Today we would like to show our Sap Flow Sensors. Our sensors are able to measure water flowing through the stem indirectly using the heat pulse technique. So far, we've seen that our gauge design works really well as our theory behind it and the whole system integration. So we think that these sensors are an excellent tool for real-time monitoring of plant water consumption. These are a do-it-yourself sensor. They are easy to build and very easy to install. So let me show you how we do that in the field. Thank you for following me up to the field. Now we're going to hear from another researcher, Manny de Leon.
How you doing? My name is Emmanuel de Leon. I work with the CSU Agricultural Water Quality Program. Our mission is to implement targeted best management practices that can improve and reduce nutrient and sediment loading in our water bodies. We evaluate best management practices by quantifying the amount of sediment and nutrient abatement that best management practice can have. In addition, we also got a CIG grant, which stands for the Conservation Innovation Grant, that will allow us to build our own low-cost water sampler. For right now, the industry standard costs close to $10,000, but our plan is to reduce that cost to something about closer to $700 that will have the same functionality as our standard edition. Next, you'll hear from Ian Asklin, second-year grad student under Jay Ham.
Hello, my name is Ian Brazil Axland, and I'm a graduate research assistant here at CSU, and I work really closely with Dr. Jay Ham and Dylan Casey, who's also a GRA. We focus on measuring the environment, specifically microclimates, and creating open source, low-cost technology that's also IoT. And primarily what I've been tasked with and specialized with is soil moisture sensors and installing them across Fort Collins on both turf and agricultural sites. The device that I'm holding today is a soil moisture data logger. So one of the main components to our lab that we use with all of our projects is trying to keep things open source and also low cost. And so low cost is an important part to this. Making sure that we stay around 10 times lower than something that's commercially available is kind of what we aim for. Eventually, when the products are close to finished, we hope to open source them. And then also, like I said, we like to keep things modular. So in the future, people can change out parts, change the antenna, change the battery. If they want to connect with Wi-Fi instead of cellular, they can change this particle board to something different. And so those are kind of the ideas we have to try to keep the device updated. So in the future, if people decide they want to change it, they can. It's also affordable, so if they want to change it, they can. Thank you everyone for joining us for our virtual IIC Field Day. A special thank you to all the researchers and graduate students that put so much time and work in out here this summer. And we look forward to another great year next year.
And here we are, we finally reached the end of our first ever IIC Headquarters virtual field day. If you'd like to learn more about the Irrigation Innovation Consortium, I'd just like to point out that you could find out about us on social media outlets such as Twitter, Instagram, or Facebook. And if you'd like to find in more detail about these projects in particular, you can find out on our homepage, irrigationinnovation.org. Thank you for joining us, and we'll see you next time.